A power transformer is often the most expensive and critical asset in a substation grid. It provides the essential interface between high-voltage transmission and the local distribution networks that power industry and homes. The standard method for guarding an asset like this is differential protection. This relies on Kirchhoff's current law. The current entering a protected zone must perfectly equal the current leaving it. This is known as ANSI 87, the standard device number for differential protection. If that equation does not equal 0, the protection relay assumes current is escaping through an internal short circuit. It instantly triggers a trip to isolate the equipment. A power transformer is explicitly designed to alter voltage and current. The current entering the primary winding will never naturally equal the current leaving the secondary. The first culprit causing this false differential is the vector group phase shift. In a standard delta-Y connection, the physical wiring of the coils shifts the output sine wave 30 degrees out of phase with the input. A raw comparison of these currents yields a massive mathematical error. The second culprit is the on-load tap changer, or OLTC. An OLTC is a mechanical device that physically adds or subtracts winding turns while the transformer operates to regulate voltage. Every tap movement alters the baseline current ratio. The third issue is zero-sequence current. An external fault on a grounded Y winding can draw zero-sequence current into one side of the transformer, but a delta winding on the other side will block that current from exiting. A misoperation needlessly shuts down a section of the grid. Conversely, a failure to trip allows thousands of amps to feed an internal arc, rapidly culminating in a tank rupture and oil fire. Protecting a transformer requires a departure from simple current comparison. Engineers must deploy a sophisticated architecture of mathematical compensation, adaptive restraints, and physical failsafes. The solution begins with ampere-turn balance. This principle dictates that the product of the current and the turns on the primary winding must equal the product of the current and the turns on the secondary. Historically, achieving this balance required physical hardware. Technicians wired external interposing transformers to manually correct the phase shifts before the currents ever reached the electromechanical relays. Modern microprocessor relays handle this internally via software. They route the raw current measurements through a compensation matrix, which mathematically realigns the 30-degree phase shift of a delta-Y transformer in real time. This matrix also addresses external ground faults. When a fault occurs on the Y side, zero-sequence current flows into the transformer and circulates continuously inside the closed delta winding. The relay's compensation matrix mathematically eliminates this zero-sequence current from the differential calculation. By filtering out the trapped circulating current, it prevents a false trip. Even with perfect phase and zero-sequence compensation, physical measurement errors persist. Current transformer manufacturing tolerances and the constant movement of the tap changer guarantee that the operating current is never perfectly zero. Matrix compensation aligns the theoretical math, but the relay still needs a mechanism to tolerate the unavoidable physical measurement errors of the real world. To manage these discrepancies, the relay calculates a restraining current. This baseline measurement, typically the maximum current entering or leaving the transformer, biases the relay against tripping during heavy external loads. The relay issues a trip command only when the differential current exceeds a specific percentage of that restraining current. This graph shows the percentage bias differential characteristic. Graph A illustrates slope 1, which is typically set between 15 and 30%. This shallow slope provides enough leniency to ignore minor errors from tap changers during normal load. This logic is tested by massive external through faults, pulling immense current entirely through the windings. These spikes force current transformers into magnetic saturation. A saturated CT cannot accurately output primary current, sending a distorted waveform that registers as a false differential. To manage this, modern relays deploy a slope 2 characteristic. As seen in Graph B, the relay automatically shifts to a steeper setting during high fault currents, aggressively desensitizing the relay to false differentials from CT saturation.
The dual slope characteristic allows the relay to remain highly sensitive to minor internal faults while remaining secure when external grid disturbances distort its sensors. The most significant non-fault event for a differential relay is the exact moment a high-voltage circuit breaker closes to energize a dead transformer. An unpowered transformer core retains a residual magnetic bias. When grid voltage is applied, the core's magnetic field oversaturates. This causes the transformer to draw a massive asymmetrical surge of power known as magnetizing inrush current. Because this inrush current enters the primary winding but does not exit the secondary, the relay sees a massive current imbalance. To the raw differential equation, this is indistinguishable from a catastrophic internal fault. A genuine electrical short produces a clean 60 Hz fundamental frequency. However, the asymmetrical shape of magnetizing inrush current produces a second harmonic frequency, oscillating at 120 Hz. Relays use a logic gate called harmonic blocking to monitor this ratio. When the second harmonic exceeds 15 to 20% of the fundamental current, the relay recognizes the inrush signature and inhibits its own trip command. Relays also monitor the fifth harmonic to detect stationary overexcitation, or overfluxing. This occurs when the voltage-to-frequency ratio spikes, heating the core and requiring a distinct thermal protection response. By analyzing the harmonic content, the relay distinguishes the temporary physics of a magnetic core waking up from the destructive reality of an electrical short. Even with advanced compensation and harmonic filters, the electrical differential scheme retains a specific blind spot, an internal ground fault located extremely close to the neutral point of a Y-winding. The electrical potential near the neutral point is very low. An insulation failure here pushes minimal fault current, falling completely beneath the relay's pickup threshold. This gap is covered by the restricted earth fault, or REF relay. REF is a high-sensitivity protection scheme that compares residual phase currents directly against a physical neutral CT. Electrical faults are the final stage of a failure. Winding insulation slowly deteriorates from thermal and mechanical stress long before it violently arcs. To catch this incipient physical degradation, engineers rely on the Buchholz relay. This is a mechanical device mounted directly in the oil pipe connecting the main transformer tank to the conservator. When minor internal overheating occurs, it decomposes the insulating oil into hydrogen gas. This gas rises, displacing the oil in the upper chamber of the Buchholz relay. This drops the top float and triggers an early warning alarm. If a severe internal short circuit occurs, it rapidly vaporizes the oil, creating a massive, violent pressure wave. The violent surge of oil physically slams into the relay's lower float, instantly tripping the breaker before the main tank can rupture. While electrical relays rely on math to clear active arcs in milliseconds, the mechanical relays provide a physical check against a degrading environment. Transformer security is a layered matrix: high-speed differential relays for primary clearance, REF schemes for high-sensitivity ground faults, and Buchholz relays for physical gas and pressure surges. Because the system relies on interconnected current transformer polarities, precise matrix math, and slope calculations, a single reversed wire during installation will cause a false trip. Rigorous commissioning is required before a transformer is ever connected to the grid. This process begins with secondary injection. During secondary injection, technicians inject simulated fault currents directly into the digital relay. This proves that the software's dual slope and harmonic blocking logic function exactly as designed. The final physical test is primary injection. Massive currents are pushed directly through the high-voltage bushings to verify the external current transformer polarities and physical wiring match the relay's internal software matrix. The protection scheme is designed to clear internal faults while maintaining the asset's uptime during external grid disturbances. Transformer protection combines mathematical theory, adaptive algorithms, and physical fail-safes to secure the massive inductive components that sustain grid stability.